We now move to molecules that contain carbon-carbon double bonds and talk about how to name alkenes. And as we're going to see, the rules are going to depend a little bit on what other functional groups are present. As we start to look at different functional groups, we can see that some have priority over others. But let's start simple. The basic rule for alkenes is that the ending is -ene, E-N-E, just like the ending was -ane for alkanes. Okay, before we get into the systematic nomenclature of alkenes, there are 3 alkenes that I think it's important that everybody know the common names for. And those are ethylene, the 2-carbon alkene, propylene, the 3-carbon alkene, and isobutylene, one particular isomer of a 4-carbon alkene. If you were to name these systematically, ethylene would be ethene, and propylene would be propene, and isobutylene would be 2-methylpropene. But these are actually fairly common molecules. All of them are gases. Ethylene and propylene are both used as feedstocks for making plastics. You've probably heard of polyethylene and polypropylene. And they're commonly ordered from gas suppliers by saying, I would like a tank of ethylene or I would like a tank of propylene. If you call the supplier and said, I would like a tank of ethene, they may be able to figure out what you're talking about, but then again, it may take them a couple of minutes and they'll say, oh, you want ethylene, right? So that's why, as a good practicing organic chemist, you should be familiar with these 3 common names because these molecules always go by those common names. So when we're going to name an alkene systematically, we've got 2 rules that we have to keep in mind, at least for simple alkenes. The first one is that the parent chain is the longest chain that contains the double bond. And the second rule is that we need to show where the double bond is in the chain by using a number. Okay, we only use the double bond is between 2 carbons. It's always between 2 carbons, but we're only going to use 1 carbon number to denote the position of the double bond. And we choose the number of the carbon closest to the beginning of the chain. An example will make this clear. How many carbons do we have? 1, 2, 3, 4, 5, 6. Where is the double bond? Between carbon 2 and carbon 3. So since there are 6 carbons, this is going to be a hexene, and because the double bond is between carbon 2 and carbon 3, it's going to be 2-hexene. Okay, next example, slightly more complicated in that we have substituents present also. Okay, so the double bond is going to take priority over simple alkyl substituents. So in this case, if we numbered the molecule from left to right, the double bond would be between carbon 3 and carbon 4. But if we numbered the chain from right to left, the double bond would be between carbon 4 and carbon 5. We want the double bond to get the lowest possible number, so we're going to number this chain from left to right. Therefore, it is a 7-carbon chain. It's a heptene. The double bond is between carbon 3 and carbon 4, so it's called a 3-heptene. And then there are 2 methyl groups at carbon 6, so the full name is 6,6-dimethyl-3-heptene. If we have a cycloalkene, this brings us to rule 3. We're going to want the double bond to be between carbon 1 and carbon 2, unless an alcohol is present, in which case the alcohol, because it takes priority over a double bond, is going to get carbon 1. Other substituents then should get the lowest possible numbers because the double bond takes priority over other substituents, alkyls, halides, etc. Okay, so let's look at another example, example 3 here. So we have a 6-membered ring, so it's a cyclohexane, except it has a double bond in it, so it's a cyclohexene, and it has 2 methyl groups coming off of it. Okay, so what's our numbering scheme going to be? Well, we said the double bond is between carbon 1 and carbon 2, therefore we have one numbering scheme in which we go around the ring in the clockwise direction, that puts a methyl group at carbon 3 and another methyl group at carbon 5. This turns out to be the correct numbering scheme. We want to go clockwise around this ring. If we went counterclockwise around this ring, the double bond would still have to be between carbons 1 and 2, but now the methyl groups would be at carbons 4 and 6 instead of at 3 and 5. So we go clockwise around the ring to give those methyl groups the lowest possible number. Therefore, this molecule is 3,5-dimethyl cyclohexene. Okay, now we get into the really hairy situation where you have both an alkene and an alcohol in the same molecule. And here's an example of how a molecule like this would work. So we have to indicate three things. First of all, where the substituent is, which in this case is a methyl group. We have to indicate where the double bond is, and we have to indicate where the alcohol is. And if you're following me, we're running out of places to put numbers. Okay, it's a 5-carbon chain. It's got an alcohol at position 2. It's got an alkene at position 3. Remember, the alcohol has to get the lowest number. And then it's got a methyl group at position 4. Well, the way we handle this is we put the number for the alcohol right before the OL suffix. Okay, so this molecule then is 4-methyl 3-pentene-2-ol. Okay, so that 2 right before the OL is telling you where the alcohol is. You may not like this. I didn't like this the first time I saw it. It seems kind of hokey. But you know what? It actually works because we have a specific place to put the position of the double bond, and we have a specific place to put the position of the alcohol. Okay, one other thing that we need to be aware of when we're talking about groups that have double bonds is sometimes, especially if it's a rather complex molecule, you will find that there are double bonds on a side chain. And there are two simple cases of side chains with double bonds that we need to be able to handle. One of them is called a vinyl group. Okay, in this particular drawing, I don't actually want the main chain to be an 8-carbon chain. I just have a chain there to indicate that that's the main chain of the molecule. For us to want to name it this way, that main chain is probably going to have more complexity to it than just a hydrocarbon chain. But if you have a 2-carbon substituent where between those 2 carbons is a double bond, that is called a vinyl group. Okay, and vinyl is something that I'm sure you've heard of. In the way olden days when I was a little kid, cars had vinyl seats. You may have heard of these music recording devices called records that are sometimes referred to as being vinyl because they are made out of vinyl. And you may have also heard of PVC. Well, the PVC stands for polyvinyl chloride, where vinyl chloride is the monomeric unit that's polymerized. Okay, so vinyl can be used as a substituent on a larger ring, or it can be also used as the common name in a molecule like vinyl chloride. Insert one more carbon to give you a 3-carbon substituent chain with the double bond between carbons 2 and 3, and that is now called an allyl group. And once again, you can have, 4 allyl what have you on the chain, or allyl can be used as the first name of a common name for an alcohol, for example. So this molecule would be called allyl alcohol. Okay, so vinyl and allyl, 2-carbon, 3-carbon side chains that contain double bonds.